Let me break it down. So when we rotate the device, two things must happen in the background. First, of course, we have a change in resolution, but as you can see here, unless we manipulate the image to adapt to this new orientation, the display processor will try to draw from this origin, and that will mean that it will have to either stretch the image or maybe crop it for it to fit in the renderable area. So by manipulating the image, by performing this rotation, we move the origin to the right place, and this is what the user will expect. Let me do it with a bit more detail. So let's say we rotate this device. First, there is a change in resolution. So as you can see, this is just a matter of hiding some detail in some areas, exposing some other. And then, unless we actually rotate the frame, it won't look as the user expects. And this is very obvious. You might think, why didn't I have to worry about this until now? And the reason is this has all been happening under the hood by OpenGLES drivers. They were being able to detect these orientation changes and perform this for you at almost no cost. However, Vulkan drivers simply cannot make the right assumptions to do this for you. And that means that the responsibility of rotating the frame falls directly onto the application. Still, most presentation engines will claim support of different orientations, but that doesn't mean that this comes for free. In the case of Android, the Android compositor will perform an extra rotation pass if the application hasn't done the rotation, and this extra rotation pass is quite costly. It might not directly impact FPS, but it will definitely take power and, of course, impact battery life. The recommendation, therefore, is that you move the rotation to the application, something that we call pre-rotation. So you don't need that extra pass. You're basically drawing everything at this new orientation, which makes the compositor pass redundant. And in the code, it is a matter of monitoring the orientation of the surface. And it is also, when you are acquiring a new image, you can detect a swap chain out of date error. And when you recreate the swap chain, then you just need to ensure that the pre-transform value in the swap chain matches the current transform value of the surface. If you do this, you are communicating to the compositor or presentation engine that the application is taking care of the change in rotation, in orientation, and nothing further is needed. And this is what the sample exposes. As you can see at the bottom, we have a checkbox to enable and disable this pre-rotation path. Of course, if you are doing pre-rotation, that means in most cases, what you're doing is modifying the projection matrix in the vertex shader, so it doesn't introduce any extra passes. And then at the top, we show in this case, the write and read stalls, which are cycles that the GPU is waiting for some load store operations because the memory bus is busy. And in this particular device, the reason is there is a separate block that is handling the rotations and making use of this memory bus. And as you might notice, these benefits are not as big on this video because actually the screen recording application is also making use of the memory. But I have a device with me running the demo live, so if you're interested, I can show you after the talk that sometimes we hit up to 90% reduction in memory bandwidth, which is, of course, good for battery life. Another caveat is that this might not be the case in all devices. In fact, increasingly more devices include a display processor that is capable of performing this rotation in hardware, which, again, has no cost. But you can simply not assume this will be the case in all devices. And in those that don't, this kind of optimization is where it plays a bigger role. And another sample is the one dealing with attachments in render passes and how to correctly set the load store operations. When you are setting a load operation, you have several options. You have load, clear, or don't care. And in load, what you're saying is that how the GPU should allocate memory. In this case, we want the memory to be preserved between render passes. And that has its use cases. Most of the time, though, you won't need the previous contents, so you can basically clear the contents with a uniform color, which is the load up clear. And don't care, you are treating it as undefined. The idea here, in the tutorial, we take you through these three options and we explain when to use which. And this is very important because, as was mentioned as well in the panel earlier, this can go into very costly read and write operations that are essentially not needed. So just make sure that you use the right one for the right case. Similarly, for store operations, you have a choice between store and don't care. And in the case, for example, of the depth attachment, most of the time you won't need this in further passes, so you can also set it to don't care. And the sample allows you to play around with different combinations of these values and monitor the effect they have on the bandwidth again. In this case, you can sort of estimate how much bandwidth you're saving using the data that we also display in the GUI at the bottom. You have the resolution, you have the bits per pixel, and the current frame rate. So you can estimate around 300 to 400 megabytes per second, and that corresponds to the change in the curve that we see as we play toggle between load and clear and store and don't care. This is, of course, for an uncompressed frame. And speaking of frame compression, the last sample I wanted to talk to you today is the AFBC. This is an ARM technology. The ARM frame buffer compression is a protocol and format for compressing frame buffers. And this is not something that you have to explicitly enable in Vulkan. This is, if it is supported by the device, you should take advantage of it at no cost. But the problem is there are certain combinations of initializing your images, image views, that may make AFBC not capable of kicking in. So in this tutorial, what we go through is the setting up of your swap chain and images, and if there are certain features that you don't really need, just make sure that you are setting the right values to take advantage of AFBC, which, as you see in this case, as I enable AFBC, you can see a reduction in bandwidth, which roughly corresponds to 30% savings. Next, I want to talk about the framework that is underlying these samples and how you can create your own samples as well. So as I said, we take benefit of the cross-platform, and you can run it on desktop for debugging. We also introduced some sort of abstraction, but in this case, we didn't want to create like another game engine, right? What we're doing here is just provide the right level of abstraction so that the samples are very easy to read, and that we expose the behavior that we want to override to demonstrate a particular best practice. We also take advantage of some of the tools that the ecosystem provides, like SPERV Cross for shaded reflection. And we use it to automatically generate some of the structs. And we also integrate a GLTF importer, and hopefully this will be useful for you to import your own assets or scenes and run the samples on them. Our own entity component system also allows us to give behavior to some components like the first-person camera. And the scene graph, we're still working on it because we want to use it to show some optimizations like batching, interleaved attributes, and front-to-back rendering. So for a simple Hello Triangle application, you might see something like this. You have to set up your Vulkan objects first, and in orange, I outline the dependencies between them. And this is something that you will have to manually set up yourself. But with our framework, what we try is to do some of this for you and handle this in a dependency hierarchy. Again, as I said, with SPERV Cross and GLSLang, we can also parse the shaders. And in blue, I highlight many of the objects that we can pre-populate for you with straightforward information like shader stage and type. So then, when you have this object set up, you can then start to record into the command buffer. And we also give some helper functions to keep it to a minimum, the sort of housekeeping that you need to do with dependencies, for example. And we provide certain abstractions that allow you to combine like images and image views into render targets, and then these ones make up a frame. And for a simple triple buffer application, then you have 3 render frames in your render context. So in an example like this one, where you have multiple render passes performing shadows, off-screen post-processing, and then final composition with the GUI, what we try to do is make the sample very readable and hide away much of the boilerplate. We also have some helper functions for begin and ending a frame. For example, begin frame deals with things like swap chain recreation. So again, this framework, what it aims to do is to still keep it very close to the API, so we don't magically do many things for you. What we do is try to expose the right behavior at the right time. So each sample, if you need to, for example, in the load store operations, override this particular render path creation, then we make it very explicit and very easy to read and follow along. In terms of samples, we also have a hello triangle sample. This one doesn't do any of this abstraction for you, so you can see when you get started exactly these first 1,000 lines that you need to get going. And then from there, we take on the other samples that hide more and more. We also have a sample showing the benefit of pipeline caches, and another one going through how to set up the pipeline barriers correctly. And these are some of the other samples that we have in the backlog, but since we released it at GDC, we are having some people cloning and giving us feedback, and we have more requests, so we'll be reprioritizing this. And of course, since it's open source, I encourage everyone to check them out and give us feedback or even pull requests. So as I mentioned at the beginning, we also have our own tools for performance profiling. And also at GDC, we presented a new set of performance analysis tools under ARM Mobile Studio. So as I said, ARM Mobile Studio, these tools are now targeted to Android developers. So this is a shift in focus for ARM, since we usually targeted our tools to silicon partners and device manufacturers. But now we are focusing on developers, and the main requirement for this market is that developers want to focus on developing their game. So tools should be easy to use and easy to deploy, particularly on off-the-shelf devices, so no need for routing, for example. And the advantage of some of these performance analysis tools like ARM Mobile Studio is that they give access to a much wider range of performance information than just FPS tracking. Counters and sensors built on the device give you access to logical events, such as cache misses or memory traffic, and even analog behavior, like the thermal condition of the device. But why should you care about performance? Reason number one is creating an appealing game, right? User retention is very clearly correlated with performance. Analytics data from some of our game partners show that just an increase in 25 to 30 FPS translates into a 50% increase in user retention. Secondly, we also want to target a wide range of devices, and this means making our game run efficiently on both a mass market device and the super latest high-end phone. And this means, well, on high-end phones, you might reach console quality graphics, but you are always under this 2.5 watt power envelope. So you need to ensure that you maximize the visual impact of every joule you spend on either processing or memory bandwidth. In terms of why optimize for ARM CPUs and Mali GPUs, we have a large installation base. We are actually present, CPU technology is present on 95% of smartphones and tablets. And last year only, we shipped more than 1 billion chips containing Mali GPUs. Also, ARM is working hard on introducing features that help developers maximize their performance with the budget power available, and things like dynamic queue that combine big cores with high peak performance with little cores with lower peak performance, but that are much more efficient, provide this sort of functionality. So ARM Mobile Studio, it contains 4 tools, although only 2 of these are in the bundle that we released at GDC. Streamline, which is our system profiler for CPU and GPU performance, and Graphics Analyzer, which is our API debugger for both OpenGLES and Vulkan. As a separate download, we also offer the Mali offline compiler. This is for statically analyzing shaders. And also, we are working on Performance Advisor, which will come early next year, and this is our solution to automating tests for your continuous integration workflow. So I'll go into this in more detail now, starting with Streamline. It consists of 3 core tools. We have a software analyzer for identifying hotspots in the application native code. We also have a viewer for event viewer for if you have annotations in your application or if you have instrumentation. And the core functionality is the sample-based profiler. So with Streamline, you can perform a live capture of your application and see in real time all the different values for the performance counters available. And you can, as you profile, you can very quickly identify where the bottleneck is, if either your application is CPU bound or GPU bound, and in case of being GPU bound, if you need to maximize your efforts in optimizing vertex or fragment. So once you have an idea of where to look at, you can also run your application through the graphics analyzer. Graphics analyzer will capture every API call and allow you to step through all the render state and the output, so you can see the difference between what you're telling the GPU and what the GPU is actually doing. And we also allow you draw call by draw call to see the results in terms of geometry or what you're being rendering. And also we have debug rendering modes that allow you to see overdraw or shader utilization. And regarding shaders, you can also run them through the offline compiler. And this gives you, well, first of all, it checks the syntax of the shader, so it gives you an idea that your shader is sane. And then it gives you the longest critical path and breaks it down into different functional units. So you can see if you need to optimize the shader in terms of arithmetic or load store or texture operations. And this is actually also integrated in the graphics analyzer. So then it's very easy to sort the shaders from the heaviest to the least heavy. And since Android does not impose a specific level of data access in all devices, we find a situation where not every device is supported off the shelf. But that's why we are putting together a list that we have in our developer website with all the devices that we have tested internally and that we know for sure that the tools run well. And if if you're a device manufacturer and you want to be added here, then we also have a set of conformance tests to add, and we intend to keep growing the list. And this is what the roadmap looks like for the rest of the year. We have a focus on ease of use and on, as I said, adding new devices to our support list. And you can download our mobile studio for free from developer.arm.com/mobile studio. So to recap, we have a set of resources that we hope prove useful to learn Vulkan and to make sure you get the best practices right in your engine or in your game. Starting with the best practices for mobile developers in GitHub. This is, as I said, open source, and we're still working actively on it to keep adding new samples. This all came out of our PDF best practice guide for OpenGLS and Vulkan, and we will be getting more content out of that into the live demos. As I said, the tools are available on developer.arm.com/mobile-studio. And if you want to know more about the tools, this was just a taster of a webinar that we are running in a couple of weeks on April 23rd. This is being run by one of our performance analysis experts, and it will go in much more detail through both Streamline, Graphics Analyzer, and how, with real examples of how you can use it for a particular need. We also have blogs that touch on the different tools. And if you have any questions or you want us to give you a hand with performance analysis, we are also reachable at developer@arm.com. And of course, the compulsory we are hiring message. We have several positions in Cambridge. We are looking for team leads that will focus on optimization for game engines and on developer education. So if you're interested, also grab me after the talk. We can give you more details. Thank you very much. Any questions?
Hello, not sure if you can answer that, but is it possible to query whether a device has this hardware rotation feature or not?
I don't think it's possible to query directly, but you can, if you run our sample, you will see when you toggle between the two modes, if you see any difference in performance, that will be an indication.
Yeah, but then I have to test all the devices.
Yeah. Another thing, No, from the top of my head, I cannot think of a specific query because it's just a matter of Android developer options allow you to force GPU composition, for example, but not from Vulkan itself. You can monitor the current transform, but as I said, you can also query if the presentation engine supports the different rotations, but if it says it supports it, it doesn't mean it supports it efficiently. So it will do the rotation for you, but it might have a cost.
Okay. Maybe you add this to your supported device list.
Yeah.
Thanks.
Thank you.
Well, if there's no more questions, let's thank the speaker one more time.
Thank you.